In this next example, we're going to look at optimization using volumes and surface area. A cylindrical can is made to hold 1 liter of oil. Find the dimensions that will minimize the cost of the metal used to manufacture the can. So really what this is asking us to do is to find the smallest surface area for a cylindrical can that can hold 1 liter of oil. Okay, so here's just a quick sketch. So cylinder, then the important dimensions for a cylinder would be the radius and this dimension right here, the height. So key, I'm just going to let r equal the radius and h equal the height of the can. Then the volume for a cylinder is the area of the base, happens to be a circle, pi r squared, times the height. And for this particular can, the volume has to be 1 liter. So 1 is equal to pi r squared h. What am I trying to do? I'm trying to minimize the cost to manufacture that can. Well, when I manufacture the can, I need the top of it, circle, the bottom, another circle, and then I need the sides. And if I cut this and open it up, I'm just going to get a giant rectangle. Then I'm going to be adding up all of these 3 pieces. So the surface area is going to be the area of this circle, pi r squared, it came from here, plus the area of this circle, pi r squared, because it came from there, plus the area of this rectangle. Well, if I want the area of a rectangle, I need the length times the width. And this width here is just the height of the can. What's this length? Well, that would be the circumference of this circle. So circumference, which would be 2 pi r. So the area for this rectangle is length 2 pi r times width, which is height. So our surface area is 2 circles, that is 2 pi r squared plus 2 pi r h. And if I want to minimize this, then what I want to do is take the derivative and find out where it's 0 or undefined, and those will give me my optimum points to check. Of course, we all can see that the radius and the height, those variables have to be greater than 0. Okay, so using this piece of information here, let's solve for h and substitute into there. That is 1 over pi r squared is equal to h. Then this value here can be put in there. So surface area is equal to 2 pi r squared plus 2 pi r h, and h is 1 over pi r squared. So simplifying my formula before trying to take the derivative, 2 pi r squared plus 2, the pi's cancel, r cancels an r, I've got 2 over r, or 2r to the minus 1. Okay, now we're going to minimize. So take the derivative, and remember pi is a constant, 2 pi is a constant. So leave the 2 pi out in front, take the derivative of r squared, and I get 2r. So 4 pi r minus 2r to the minus 2, or 4 pi r minus 2 over r squared. And I could give this a common denominator by multiplying by r squared over r squared, which would give me r cubed over r squared. So S prime, surface area prime, is going to be 0. Of course, we know it'll be undefined if the denominator is 0, but that wouldn't make sense. It's 0 if our numerator is 0. So the derivative is equal to 0 if 4 pi r cubed minus 2 is equal to 0. Two over 4 pi gives me 1 over 2 pi, and cube root of both sides. So if r is equal to the cube root of 1 over 2 pi. Okay, asked to find the dimensions means we need the radius and the height. So put that r value in to your height formula, cube root of 1 over 2 pi. And for homework, I want you to simplify this for me. The height should be 2 times the cube root of 1 over 2 pi.